Okay, so starting the recording, record on the cloud.
Recording in progress.
Okay, good. Start this. Ding. Okay, so today we're going to talk about sort of what use is this P versus NP stuff. Now, fundamentally, I mean, if you don't understand P versus NP, then you don't really understand computer science. I mean, this is like if people say, oh, well, if you were in chemistry, nobody would say, why do I have to know, you remember, like hundreds of years ago, people tried to turn lead into gold. And you can't do that with chemical reactions because they're elements. Right? But what if somebody said, well, why do I have to know why you can't turn lead into gold? What's the use is it to know that you can't do something? I'm interested in the stuff you can do. And you actually hear people talking about P versus NP this way, and they're like, yeah, well, I don't care. Maybe you can do clique and poly time, but if the exponent is really big, then it doesn't make a difference to me. Okay, people who say, why does it matter? Why do I have to learn why you can't turn lead into gold? They don't understand chemistry, and they don't seem to want to understand chemistry. People who say, well, why does it matter that, if we can do clique and poly time, if maybe the exponent is really big, they don't understand computer science, and they don't really want to understand computer science. If you don't understand why you can't go faster than light, and you're not curious about that, and you don't want to know, and you're only interested in the stuff you can do and you can make money from, then you're not really a physicist, right? So it's like, okay, if you're going to be a computer scientist, well, we haven't actually proven this one way, but you should understand that this seems to be something interesting going on with this P versus NP stuff, that all these problems seem to be equivalent. If you can find a polytime algorithm for one of them, you can find a polytime algorithm for all of them. That seems to be interesting. Anyone else? Anyone else what? What? My internet is... okay, I'm going to switch and try to connect through my phone. This means I'm going to disappear for a second. I don't know why my internet is so bad. This is really going to burn down my data, but okay. Okay, so I was saying that that people ask, one free hour. I have Kudo on my phone and Eastlink in my apartment. Tethering portable hotspot. But I never use my data anyway, so I should be fine. So now, I don't know why this... Okay. I'm going to switch over to the phone, so I may disappear for a second. Can you see me? Okay, so this is going through the phone. We hope this works. Okay, so yes, one of the reasons, so in this book, actually, if you look at the scribe notes from last year, so in this book, there's this description of, there's a cartoon, which I should have looked up earlier, of the Bandersnatch problem. Right, here it is. Oh, right, it's on page 2. That should have been easy to find. So what happens is they're saying, well, one of the reasons they said one of the reasons to study this NP completeness stuff is so that you just don't keep. This is the Gary and Johnson Computers and Interactability Guide to the Theory of Incomplete. Everyone just calls it Gary and Johnson. Nobody ever says the title. Gary, G-A-R-E-Y, Johnson, Johnson with an HN. Okay, so they say, suppose that you find a problem and you can't find an algorithm for it. Well, you don't want to be in the first figure where it says, I can't find an efficient algorithm, I guess I'm just too dumb. Right. So if for example, and then if you could do a reduction from the halting problem to your problem, so show that if you could solve your problem, then you could solve the halting problem, then you can say, I can't find an efficient algorithm because no such algorithm exists. Right. Or if you could actually unconditionally show that something is. Now there are actually problems that we can show that, like the halting problem. I haven't talked about any of the other ones. There are problems that we can solve, but which you can't solve in polynomial time. So if you can say that, great. Then you're sort of off the. I mean, you're not exactly off the hook, because then your boss is still going to want you to do something. Like, there are problems we have to solve, and I'm worried. Yeah, it seems to still be connected. Okay, there are problems we have to solve, and like people are saying, oh, like we need this, and you're like, too bad, it's impossible. And they're like, well, what can you do? You can do approximations. You can deal with deal with special cases. You can, you have heuristics. So then you fall back on not trying to find an exact algorithm. But that doesn't happen that often, that you can actually prove unconditionally that there is not a polynomial time algorithm for the problem. Like, we can't prove that for SAT or clique or independent set or HAMPath or whatever. We can't prove that P is not equal to NP, so we can't actually, so I mean, yeah, fine. If you can prove P is not equal to NP, great. But usually what you're aiming for is this last one that says, I can't find an efficient algorithm, but neither can all of these other people. So you can now say, look, for 50, if you go out and you get a job and your boss gives you a problem, then and you can't find a solution after a week, you turn around and you see, okay, is this NP hard? You try to do a reduction. Is this NP? Okay. You try to do a reduction from some problem you know is NP complete to this problem, and if you can do that, you can say, okay, you can't. I'm unlikely to find a polytime algorithm that gives you an exact solution. People still there? Okay, so this actually, okay, good. So this actually does happen. I mean, your boss is, if they're a manager or something, they haven't done computer science, these problems, there are hundreds of problems in that book that people have actually tried to solve and which we now don't try to solve exactly because we've managed to show that they're NP complete. So for example, a few years ago, I was at the University of Helsinki, and a friend from Japan was visiting, and she wanted us to work on this problem. Given a string, can you partition it into the minimum number? Can you partition it into palindromes, palindromic substrings, such that each palindrome is unique? And she said, okay, let's work on that. I think we can do it. And two of us said, that sounds hard. So, but she kept insisting that we should work on this. So finally we said, look, okay, we 9 of us got together in a room, and for 3 hours we hacked at it, and we proved that it's NP complete. We reduced, obviously it's in NP because given a solution, yes, you can check it. Given a partition, then you can check each substring as a palindrome and that they're not equal. But we reduced circuit sat to it, which, we got a paper out of it. It's brutal. Said don't do this. So yeah, if your boss gives you a problem and you say okay, well, in order for you, and you go to it, and you go back and you say, well, I can find an approximation, and the boss says, what are you talking about, an approximation? I want an exact answer, you're fired. And you can say, well, look, you shouldn't fire me, maybe you do, but it's unfair if you do, because it's very unlikely anybody's going to find you an exact polytime algorithm. Okay, so that's, yes, there is some use. And then after you get into approximation algorithms, heuristics and fixed parameter tractability and blah, blah, blah. So yeah, there's that. To know that we can stop and you don't have to keep wasting your time. But there are also, so there are two reasons. One, you should just understand this because it's at the core of computer science. And it's like, to understand why you can do what you do, you have to understand why you can't do what you can't do. Now, when I say can't do, I'm assuming that P is not equal to NP. And to understand, I need to really understand when people talk about what does it mean. But today, I'm going to show you two things that you can do, that you like positive results that you can actually do. Well, sort of positive result. One thing you can do with NP completeness, and another thing where it's not just out there affecting problems which are hard, but it's sort of, we work in P, the class of problems in which we can solve in polynomial time, right? We think about, like, those are the things that you can do in reasonable amounts of time. And we can actually, I'll show you that you can actually use results about NP completeness to prove lower bounds on problems that we can do in polynomial time. And that's kind of new and very popular in complexity theory these days. Okay? So, I don't know if this shouldn't take the full hour and a half, but we've gone on for like 15 minutes already, so okay. So the first thing we're going to see is something called zero knowledge, okay? This is kind of cool. It's from cryptography, and actually I used to know the guy. He's a professor, another professor. Cook is at Toronto. This is another professor at Toronto. Toronto has a very strong complexity theory group. So this guy, Charlie Rakoff, he got the Gödel Prize for this, and then the two co-authors, Shafi Goldwasser and Silvio Macali, got the Turing Award for this, because it's this idea of something called an interactive proof. And this is, I mean, usually if somebody says prove something to me, you think, okay, it's a proof, and then you're 100% sure. This is sort of a statistical thing where I can convince you to any extent that you want, but you know, you're only 99.99999% sure that I'm actually not lying. Okay, so I hope you're going to understand this by the time we get through this. So, what is zero? Why is it called zero? Now, interactive proofs are lots of other stuff. Zero knowledge, technically, a zero knowledge proof of knowledge is when I want to convince you that I know something, but I don't want to tell you what I know. Now, this is, I mean, the absolute worst outcome of a course is when you think you don't know what the course is about, and you think the professor doesn't either. The best is when you come out of the course and you understand everything and you believe the professor does too. In the middle is when you believe the professor knows what he's talking about, but you have no idea what's going on. So that's sort of like, so what I'm not supposed to be doing as a teacher is zero knowledge proof of knowledge. I'm not supposed to be trying to convince you that I know what I'm doing, but I'm not going to teach you. However, just for this course, we're going to pretend that that's a legitimate objective. Okay, so let's suppose I know something, and I want to convince you, but I don't want to tell you what I know. I want to convince. So, for example, there is a graph, or there is a formula, and I tell you that it has a satisfying truth assignment. It's a positive instance of SAT, but I don't want to give you that instance. Now, why would anyone, I mean, apart from like strict, like just it's perverse and kind of fun, like do not do this on your next homework assignment. Do not try to do a zero knowledge proof of knowledge to convince the marker that you know what the answer is, but you don't want to write the answer. Don't do that. That's not cool. It's kind of cool, but don't do it anyway. But you can actually use this in crypto, right? Because suppose that what I'm going to do, I have something. I have this formula. Okay. Suppose that I built this formula ography or coin? What? I don't understand what ography question mark means. Okay, cryptography. Yes, cryptography. So I'm going to. So one of the things you sometimes want to do in cryptography is prove to somebody that you are who you say you are. Right? A proof of identity. Now there are various attacks against this, like man in the middle and blah blah. But let's suppose that I have built this formula in such a way that I know a satisfying truth assignment, and it'll be hard for somebody. I believe that P is not equal to NP, and it's going to be hard for somebody else to find a satisfying truth assignment for this. It'll take them more than polynomial time. So I have this satisfying truth assignment, and I have this formula. I publish the formula. That's public, right? So I stick it on my website and I say, I, Travis, know the answer, know a satisfying truth assignment for this formula. And I believe that other people in a reasonable amount of time are not going to be able to find this satisfying truth assignment. So if I meet you on the street and you want to know if we're at a fancy dress party or something and I'm in costume and you want to know that it's me, ask me to give you, to show you that I know the satisfying truth assignment. Now, okay, so we're at a Halloween party or something where I'm in costume and you say, you know, are you Travis? Are you my professor? And I say, yes, I am Travis. And you say, oh, well, I would like to buy my professor a drink, but I don't really believe you're my professor. And I say, well, I don't want to take the mask off. It takes so long to put this costume back on. But just believe me, I'm Travis. This has never actually happened, by the way. So just believe me. I mean, you say, I don't believe you. I think you're somebody else trying to just scam a free drink. And I say, well, I can prove to you I'm Travis because I know the satisfying truth assignment. And you say, oh, that's great. Give me the satisfying truth assignment. I'll check to see that it actually satisfies the formula. I say, oh, but if I give you the truth assignment, then you're going to know it. And then you're going to be able to go around this party and find my students and get free drinks that are actually intended for me. So this, instead, to prove to you that I am Travis, I want to show you that I have a satisfying truth assignment, but I don't want to tell you what it is. Right? So this is like when your computer connects to the bank, you want to prove to the bank that you are who you say you are, but, well, okay, I guess you trust your bank, but maybe something, you know, you want to be able to prove you are who you say you are, but you don't completely trust the other party, so you don't want to give them sort of your private key, if you know crypto. Okay, so how do I prove to you that I know something without telling you what I know? Okay, so do people know Sudoku? This was popular. I know Sudoku was super popular a few years ago, and so, yes, some people, yes, okay, it's still popular. I was gonna, actually there is, I didn't do a proof that Minesweeper is NP complete because I'm not sure people these days know Minesweeper. Like, it was popular 20 years ago. Okay, so you know Sudoku. Sudoku is 9 by 9. Who's Stanley? Sudoku is 9 by 9. So that's actually, 9 is a constant. So I could just burn through, like, what are all the possible ways to fill it? Well, there are 10 numbers, right? No, wait, that is not 9 numbers. We're ignoring zeros. Okay. So there are 9 digits. So how many possible solutions for a 9 by 9 Sudoku are there? The most 9 to the 81, which is a big number, but it's still a constant. I can't say something about the complexity of normal Sudoku, which is 9 by 9. I can say something about the complexity of n by n Sudoku. So let's suppose n is a square. So 100 by 100 Sudoku, right? Then you're going to have 100 rows, 100 columns, and you're going to have, each row is you're going to have like blocks of 10, right? So 10 by 10 blocks, and you're going to have 10 blocks across and 10 blocks down. And in each of these blocks, you can put the numbers between 1 and 100. Right? So n is 100. It'll be n by n, and n is a square, so you can have these squares which have 1 to n, and you line it, and it's like, okay, so you could generalize Sudoku. Generalized Sudoku is NP complete. You can actually, if you could solve generalized Sudoku, n by n Sudoku, you could solve SAT. Okay. Somebody has done a reduction from some NP complete problem, I don't know which one, to Sudoku. So, I'm going to show you how to do, and this is an easy proof. Right, I've actually done this to my niece years ago, when she was like very small. Suppose that I want to prove to you that I know. You come to me with a Sudoku puzzle, and you say, I don't think this has a solution. This is too hard. I've been trying for ages. I say, no, it does. I know it. And you say, I don't believe you know it. So then what I can do, now this the first I'm going to tell you is called a physical zero knowledge, proof of knowledge. I take cards. So I take n by n squared cards. So for a normal Sudoku, I take 81 cards. Okay? And on the backs, I write the positions, right? So I have, I can have like a card, and I write 3, 1, meaning that it's in row 3, column 1. Okay? So I'm going to have everything from some card which is labeled 1, 1, down to some card which is labeled 9, 9. Okay? So on the backs, I write the positions. On the fronts, I write the number that's in that cell, in the solution. Now, we lay the cards out, so there's you on that side of the table and me on this side of the table. We lay the cards out face down so that you can see that they're in the correct positions. And then I say, okay, the numbers which are showing, the numbers that are filled in the instance of Sudoku, turn those cards face up, right? So you can see that they are the right numbers, okay? And then turn them back face down, okay? Now, take each column and gather the column, so you gather the column into a little deck of cards. Okay, so now you have 9 decks of cards. Shuffle each deck. And now look at them, not looking at the backs, now looking at the fronts. Just check that each deck contains the numbers 1 to 9. What does this tell you? Okay, when they were face down, you checked that, you know, the things, the numbers that we're showing were in the right place. You've checked.